Good morning, everybody. My name is Zhen Luo from MPS. I'm a director of technical marketing and application engineering. Today we'll talk about the EMI virtual lab. And for the contents, I'll cover both conducted EMI modeling and radiated EMI modeling. And we'll talk about some case study, how we use those models to do meaningful stuff. For traditional EMI debugging and diagnostic, it's really a painful task for engineer. Because you have to pinpoint your board, sneak things wrong, and sometimes you may need to use the copper foil to shield certain area to try to see if this is a problematic area. And all those is a guessing work, and you identify those suspicious and change your PCB, and you tape out, right? And once the board coming back, you spend $2,000 at the EMI lab, and the bingo cross it will pass the EMI. But sometimes it's coming out still not enough. So it's a very frustrating process, and that's why I encourage people that using the virtual lab or simulator to quantify the noise. As long as you can understand the noise and quantify it, you'll have much more confidence that your design will pass the EMI limit. So let's talk about the model. For conducted EMI model, it's actually pretty straightforward. And from the left side is your EMI noise source. It's most of the time come from the power ICs. And you can get those parameters from your vendor, or there's a more straightforward way. You just measure on the EVB, get a SW switch form, waveform, and try to tune those parasitic to match the waveform. As long as the waveform was matched, and you get a very good noise source model. And on the middle is the PCB model and the passive components model. For the PCB model, you needed to extract the parasitic between the traces. And for the passive component model, you need to use the parasitics as well. For example, for the capacitor, you need to have the ESR and the ESL data, and that is very easy to get from data sheet as well. And one more thing you need to pay attention to is if you're using the ceramic cap, you also need to derate it according to its voltage. For example, if you're using 50 volt cap 10 microfarad, and using for 12 or 14 volt application, the effective capacitance is about 8 microns. So you need to use the effective capacitance in your model. And further go to the right is the listen. So you can also easily get a model from CISPR 25 or other standard. Basically, it's just a 50 ohm impedance. And then after that is the V-in power supply. And you also got your load, which is connected to your PCB board. On the bottom is the parasitic for the common mode noise, and basically it's the parasitic cap from your board to the earth ground of the EMC chamber, and we extract that number from our EMC lab. So once you have built this model, it's pretty much just a circuit simulation. So you basically measure the voltage at the VP and the VN. So that's to terminal that exactly what you do in your real measurements. And you can get your differential mode EMI by using the formula VP minus VN divided by 2. And you can also get your common mode EMI noise by using the formula VP plus VN divided by 2. So here is the result. We just show this as an example. So this is a 40 volts monolithic automotive buck, and we have a test condition at 12 volt, 5 volt out, and 3 amp load without filter. And we turn on the spectrum. So you can see from the comparison, the simulation result match with the measure result put it well. And you can also see the spectrum effect. So based on that, then you know your raw EMI data for the board, and now you can start to design your EMI filter accordingly to optimize your board. You can also throw in your EMI filter parameter into the simulation and see the final result of your EMI measurement. So let's talk about another more interesting case study, and that is if I need an active EMI filter in my design. So you might see some marketing campaign that's saying active EMI filter is better than passive EMI filter, right? But is this really true, or at least this is applied to your case? And the best way to answer it is we run the simulation to see for the one specific case if that's really meaningful. So this is a example that a DC controller. It's a 40-volt buck controller, and it integrated a standalone op-amp on the IC, which you can use for the active EMI filter purpose. So basically what you do is you will need to add the sensing branch, sensing cap to sensing the noise current, AC current. And then you inject back the current to try to cancel the noise. And you also need to design the compensation network both at the low frequency and at the high frequency to make the circuit stable. So a natural question coming to the mind, to engineer mind, is that those components that I add, worth it, alright? If compared to the best optimized passive EMI filter design, if this active EMI, show me much better result, then it's worth it. Otherwise, I might not need it. So, before I choose a real comparison, I want to cover this a little bit. When I read a lot of active EMI paper, that actually a lot of people they are comparing the EMI case for with active EMI and without active EMI. It's very easy for people to misunderstanding that the without active EMI case is the passive EMI, because we do still have the differential mode inductor and the input cap here. It looks like a filter LMC, right? But it's not a optimized filter, at least put that way. So of course you can see the result, with a so-called passive EMI, the noise is high, and with the active EMI, noise is low. So let's see what behind it, right? So if we can understand the physical meaning of the active EMI, we can better understand and we can find a way to compare it with a real passive EMI filter. So what we do is we're using the simulation tool or just using the model to develop the transfer gain function, noise transfer gain function. So basically we use the VDM from the listen, which is to measure the noise, divided by the noise of your board. So you have the active filter or passive filter in between, and that transfer gain is showing how much the noise that the filter can damp. Okay, you see the result here, and it's obviously, compared to the active filter can do much more damping, right? The gain is 25 dB more for the meaningful frequency range, 400K, for example, we're using for this case. And that explains actually the previous slides that you can see the noise actually for given frequency is at this level, and the gain actually determines it. So now we see this gain is really important, right? It's kind of a physical meaning, and also you can, if you see the formula, it's V divided by I, so it's the unit is resistance. So this is an impedance concept. And if you look at the curve, this is actually very similar to a capacitor can do. So high frequency, low impedance, very similar to a cap. So natural thinking is how about you replace this active filter with a cap, right? Then this is a fair comparison because for adding the cap, this is still a passive EMI filter, and we should compare that two cases. So here is a comparison, and basically what we do is we build the noise transfer function for two cases. One case is with active EMI filter, and another case is just with one cap. And the cap we choose is TDK 50 volt, 10 microfarad, size 1206, and the effective capacitance is about 8 micron at 12 volt to 14 volt range. And we get ESO and ESR number from the data sheet as well. We put it into the simulation. And let's compare the results. So on the top left, this is with that 10 microfarad cap, and you can see the curve is almost overlapping with the active EMI filter. And you can notice that some frequency range the active EMI filter is better. For example, in this 80K range, it's about 5 to 10 dB better on the active EMI filter. But you can also see at maybe 1.5 MHz, passive EMI filter is better, and also 5 to 10 dB better. And as well as in the high frequency, the FM band 100 MHz, passive EMI filter is better. So this gives you an idea, for the whole frequency range and how effectiveness is this active EMI filter compared to just one cap, right? And you can verify the result here, just to say, okay, if we pick the frequency about the high frequency from here, you can see that cap is actually better than the active EMI, and kind of verify the idea to look at the gain curve. So a few points I want to adjust here. So how about then we want to further improve the EMI at a high frequency? Easy way is you stage the cap, right? The smaller cap, you have a lower SL, better performance at a high frequency. So we can put one more 1.7 microfarad smaller, 0806. We can see another 10 dB improvement on the high frequency. And if we put another one smaller cap, the 0603, and we can achieve like 20 dB better of the EMI. So then the question comes to, okay, we can always improve the curve, right? And here's a good and better, but what is the good for your case? So it's really depends. For example, if your switcher, it's very common in our model space that we are switching at 2 MHz. So the gain that we have below 2 MHz actually doesn't matter, right? Because you don't have noise there, and it's more important you have the gain to suppress the noise after 2 MHz. And for this case, you can see we can actually use an even smaller cap. It's a 4.7 micron or 805, just one cap, and we sacrifice the performance for frequency below 2 MHz compared to active EMI filter. It's worse, but for higher than 2 MHz is actually much better. And this kind of optimized design for this specific case, right? You know your frequency of converter, and you know where is the noise band that you care, so you just filter that noise band. And using the simulation tool and using the noise transfer function, you can very clearly visualize it to design your filter properly. Okay, so the next topic is the radiated EMI modeling, and for radiated EMI, slightly different than conducted because only the common mode, the noise is effective for the radiated EMI, and how the noise mitigate is it's the same from the same source from switching node on your IC, and it's either conducted or coupled, so the coupling cap pass to this long cable, and for the 625 the cable is 1.5 meter long, so it's a very good antenna that radiates the noise, and then your antenna on the other side of the chamber will pick up those noise. So the key for radiated EMI model is we characterize the common mode current. And once we have the common mode current, we can using the transfer function for this cable to the receiving antenna. So that transfer function, since the standard is fixed, the cable length and how to configure it is fixed in Cisco 25, we can just extract that transfer function in the EMC lab and use it over and over. So result for the radiated EMI that you can see for a LED driver. This is an example for a 40 volt buck boost LED driver that we can also predict the noise pretty well from 30 megahertz to 500 megahertz. And for case study, I want to talk about how we use this model, right? So we can predict the dental watts. And the interesting way that we found to use it is actually, we can use it to identify which components or which area is most important, is dominating the EMI for your case. And this example that we basically extract the parasitics in the model, and until we only have this 2 ground impedance left. This is extracted from PCB as well, the parasitics. And we found an interesting point that if we compare this simplified model only contain the 2 parasitic, and we compare the common mode current with the measured result, it actually still match pretty well. So that means other components on this board is actually less important in this case, and that 2 ground impedance is dominant your radius EMI. So before you optimize this 2 impedance, then forget about everything else, right? Because on your board, this 2 is more important. So I want to give you a visual idea on how much is this loop component. This actually is typical, pretty well non-sync DC-DC layout. Basically you have to have this space to accommodate the controller and your fans, and that distance is creating the parasitic inductance, and we measure that is about 21 nanohenry for the ZGND1 and about 14 nanohenry for the ZGND2. It's not too much, right? But this is what you need to generate your radiated EMI. So then how we fix? As we say from layout, actually there's no more place to improve. So that we think, then let's redo the IC. Let's design the IC completely to have this 2 ground be very smaller. So this is what we did. So we basically separate noise source into 2 portions, so left and right. So and we also make it just internal, so there's no external diode or FET. This way you can get a much smaller loop here, and that means much smaller parasitic inductance. And since we have both sides, so it's basically in the parallel configuration, that your impedance is cut by half. So by doing this, we can see now the ground impedance for ZGND1 is only 1.5 nanohenry, and for ZGND2, 0.4. So compared to previous case, it's much smaller. And then we compare the gain transfer function, right, same as in conduct EMI modeling. So there's 2 noise sources here. One is from the jumping voltage. There's another one is from the jumping current. And we compare the transfer function in both cases, in both noise transfer function. The newer designed case is much lower. It's more than 20 dB lower. And another thing is so we reduce the impedance from board, and then is anything more that we can do? So here is another step. So we basically still have some wire bond impedance inside the package, and what we do basically remove the wire bond, and we using the copper connection, we call mesh connect, to directly solder the die on the lead frame, so we can get rid of this 1.9 nanohenry. And one more thing for reduce the EMI noise, and because we have 2 separate noise sources now, and the noise source itself also have some canceling effect at high frequency. You can see compared to the 2483, the newer design, the noise peak at high frequency is also have 15 dB reduction. So this is additional effect of that. And finally, combine all those results together, Now we can see the radiated EMI improvements between the first generation to the second gen is huge, right? So it's more than 45 dB reduction in the EMI noise. And hopefully give you a taste how we use this model to really design the EMI. It's not trying the narrow process anymore, and we can predict and we can know the result before we even tape out our IC or we tape out our PCB. Okay, this is all my today's topic, and any questions?